Welcome to Renaissance Charge Videos. I'm Rick Friedrich. This is a redo video that will be more comprehensive than the one I erased. I made a couple of mistakes in that video. I actually recorded it again several times and was not satisfied with the video, so we'll see how this one goes. This is the Renaissance Charge motor energizer inversion of the negative energy to positive energy for the battery. So what we're going to go over is how to invert the negative with a capacitor and a pulsar into the charging battery. We're going to invert or transduce the energy from negative to positive. Now this is a very difficult subject to grasp. It doesn't need to be, but it's because it's something completely different than what you're used to. Now I've been talking about negative energy, how I understand it, how I describe it. I don't know the exact physics of the whole thing, but I do know the phenomena, and that's all I can really share. I'm merely a hobbyist level in my understanding of things, so I don't claim to be some expert. I share what I can share for practical benefits. So I want to just briefly share a comment that was just sent to me right now, and I don't usually try and promote positive comments directed towards me, but this was something I felt I might as well share here. Dear Rick, I experimented on the negative impedances and I got it working. It's so unbelievable to experience this after so much years of searching. You probably can imagine how happy I am on this. Thank you. I walked through the valley of things that did not work and the disappointment that goes with it, but now I'm on the top of happiness, thanks to you. So that's rewarding to hear, and I get comments like that here and there. I think this is a very important subject, the negative as opposed to the positive energy. Here we're going to actually show how to do the positive, but I want to go over some things again. For those who are wondering, I think I'll probably delete the last video that I have as well, because it was about the 20 coiler and it's sold now. So I will probably delete that, and I have the 10 coiler sister of that particular model, which is made in the exact same way with Bedini's assistance, in the description of how to set it up exactly according to the original 10 coiler. So I will probably do a video over on that when I get time, and we'll probably redo that, the previous video, and go over some more details. Anyway, what we're going to look at in this video is the negative energy and just the overview of the model of the circuit, sort of the upgrades that I've included. I spent the last 3 weeks pulling my hair out trying to decide on the circuit the way I want it to be from this point onward. Not that there's not going to be improvements, but this is kind of a major change in which I wanted to share this, because we will be, I'll encourage that change for people who already have the kit. And so it's not really, this video is not just about the inversion or the conversion or transducing of the energy from positive to negative, but what's all involved in that? Why would we want to do that? And so forth. So we have another schematic here that I've changed in a couple of particulars, which we're going to look at. One of them is I have a capacitor across the input. So on the other end, so this is the input battery. So we have a capacitor right on the end of the wires. So right across the negative terminal of the MOSFET and the negative terminal of the MOSFET and the front, the beginning of the coils. And I have a low ESR capacitor that I will be including. In fact, this model is going to go out to a customer, and so is this one. And the customer has been waiting very patiently for these, but I wanted to give something that they could use in a multiple sense. They can do more than what I've been providing in the past. So that's one of the changes. And then of course we're going to have this capacitor SCR Pulsar that will also be included, but it will be optional whether you install that or not. It's just in series to the charging battery. And we'll look at that. And then we have a capacitor across the MOSFET as well. And so we want to look at each of those points. So starting, so this replaces the file that I had with the previous video, and the link will be on the description, in the video description. And so what we want to look at now is the parts additions and changes. So I spent hundreds of dollars, actually thousands of dollars in the last couple of weeks trying all sorts of different MOSFETs to do the higher voltage. So the reason why we want a higher voltage is, as I've talked about in the previous videos, we want to have, when you turn turn on the MOSFET and when you turn off the MOSFET, you have the negative energy coming into all the impedances along the charging battery path. So each cell is a negative impedance, negative resistance, in which the energy rushes in from the environment. We're not talking about amperage flow here, which would be on the input side. Like we have a capacitor across the, it's a very tiny 0.01 microfarad capacitor, high voltage capacitor across the MOSFET, which will charge up and in fact capacitors in series with the negative flow will actually convert the negative to positive. So this is what we got to understand. I've been talking to people, emailing people to try and explain this, well, for 15 years now, but more recently because of the recent videos. So I want to go over what I've shared with people on the phone and that, and so forth. Now I've already said some of these things, but let's get specific as far as I understand things. So I may be mistaken. I'm mistaken in many things. I'm aware of that. It's important to be aware of your limitations. So what we want to do is create a high voltage. We want to use high voltage parts because when you have a very sudden rate of change in a switch, so when you turn on the switch, you want to turn it on fast when you turn on the MOSFET, which we have done that with the gate driver, an 8-pin gate driver. And this is not, I mean, it's the best for the price and it's sufficient for what we're doing, the MOSFETs that we're using. But you can spend, some of my customers have spent a lot of money having faster gate drivers and faster MOSFETs, and they're getting better results, but it's going to be, you know, several $100s, and it's beyond the capabilities of most of my customers. So I have to balance this stuff out. But I have improved things here at a much greater expense, which will not change in price. I'll just absorb that extra expense in adding the parts that are far more expensive and adding more parts. So I'll be adding probably $20 worth of parts into the kit without raising the price. And for those who have already ordered the kits and waiting for their order to go out, that's what I've decided to do. That's why I've delayed on shipping those, because I wanted to make this upgrade. I wanted to be satisfied with it. So why use the high voltage parts? When you close the switch, you have a spike, and you can see sparking that can take place. And if you go back in history and you know how the story goes with when they ran the dynamos to power the DC lines, and they threw the switch, there would be like lightning bolts flashing off the lines. And you can try this experiment if you have the means to do it. And down the road, miles and miles down the road, sparks would fly off the line before the current caught up. So it's before current flow, you had this phenomena. So that's a switch closure. Okay, that's what people don't focus on. They only focus on the other switch, the switch opening, which is the collapsing of the coil. You know, and people want to try and assume that it's somehow merely positive energy, even though they call it negative, that results in all the, in other words, all the energy coming in from the battery is built up in this coil and then discharges once it's turned off. So you have X amount of energy with all of its losses in the circuit. So you only have a factor of 1 minus your losses in the circuit loop. So positive to negative, the loop here, all the energy coming out of this battery, which is the source, is going to manifest in all the phenomena that results. And then you have your losses. So in other words, you turn it on and you get said motor action. Then you turn it off and then you get a spike. Whatever happens in that spike is still the equivalent of the energy coming out of this battery, can be no more. So if we measure with an amp meter the amperage and the voltage and all the resistance and figure it all out, it should always add up according to Kirchhoff's law. But it doesn't, because here we're charging a battery at the rate that this is discharging, and we're running a motor with a load on the motor. So evidently that is not true, and I don't care about what people say about the mathematics, because I've experienced this for 15 years. So it doesn't really matter what people say. And I think, getting back to Walter Lewin and that whole controversy, which there seems to be very little support of him in his controversy. He has done that purely on a sort of abstract level, mathematical level. While he did do a demonstration, it didn't do any practical work. So the people aren't really taking it that seriously, and they're just making excuses mathematically to contradict what he's saying that he's mistaken. But when we charge a battery or run other loads while we're running the motor, such as I've always talked about, the fan, we're running the fan at the same speed, but yeah, we're charging another battery, that's all excess energy. Running at the same speed as if there was no charging battery, before and after, we get a total difference. So in people's minds, superficially, they'll look at that and they'll say, well, you were just not using all the energy that was coming out of the battery. So you've just made a more efficient system where the flyback diode was just shorting out the energy that was coming from the battery. So then you'd have to rework all the math right from the beginning to say that actually the amount of energy it takes to produce a horsepower, to produce 1 horsepower or whatever, quarter horsepower, is not actually accurate. We've been wrong all these years. It actually takes less energy to do that. And so you'd have to readjust everything. But the fact of the matter is, I can create more work through the negative energy that is totally disregarded. And Lewin didn't show that. It would have been crossing the line, no doubt. He would have got himself in serious trouble if he had tried to do that demonstration, which is what I'm doing and have been doing for many years. So in doing this, we create an opening and closing, which are both switches. Think about it that way. You notice a bigger spike when you have the collapsing magnetic field, no doubt. But there still is the moment of switch closure that is creating the event. And that's what we can see when I have this hooked up to my load, and I have a 33 volt LED, and I turn it on. The moment that I flip on, you see a pulse. It's not when I turn it off, it's when I turn it on. So you can verify that and see that there's also a spike pulse at the moment of switch closure. And that's not to be disregarded. So when it comes to the MOSFETs now, we want to turn the MOSFET on fast and turn it off fast. Of course, you know that means there's less losses in resistive losses in turning on slow MOSFET, turning it off, which is what the IGBT does, is it's slower. So I don't prefer to use the IGBT unless you do high current. But we want to turn this off fast. Of course, we're going to get greater efficiency in the operation of the MOSFET, but we are also going to get this sharp gradient, which creates a higher negative output. So it's in relation, the amount of inflow of energy from the environment is proportionate to the rate of change. And you can see that even in conventional theory, that the faster the rate of change, the more in your secondary, your transformer, the greater the output is. And that's just a very, I mean, you can get really complicated with the whole thing, but so we want a fast rate of change, and the downfall of that is that you have a very high amperage pulse that can be associated with that, which comes right immediately after. The amperage flow is immediately after the negative flow. So the negative is instantaneous, faster than the speed of light according to the theory. I haven't verified that by running beside the flow of energy from beginning to end. I can't run that fast and verify such things, but that's according to the theory that it's faster than the speed of light and flows faster than the current flow. But you have a very high amperage with a fast turn on, so you have to have a MOSFET that can handle it, or suitable protections. And that's what I've been trying to work on, to have a limited dampening effect, so you have maximum charging benefits. So if we're just talking about charging the battery without this capacitor pulsar here, and we're going to put maximum spike into this battery, then we see maximum spike. I don't want to confuse things. I'm talking kind of in general here, not very specifically, which is not then very accurate. So I'm going to correct it by saying we see the spike, but the energy is not the spike. That's the difference. The energy is, the spike is kind of a result of what's happening in the battery. It's shown on the oscilloscope. The oscilloscope is its own circuit. So the oscilloscope is not really showing you the other loop, the load loop. It's showing you its own loop. And that's what Walter Lewin pointed out as well, which is quite important to realize, that you're seeing what's happening in the capacitance, resistance, and inductance of this loop here with the oscilloscope. So you have to separate that in your mind from the actual load. Now this is giving you an indication of what's happening, but it's not part of the other loop. And that's vastly important when we get into really sensitive matters. When you're at the high school or college level, you're at a very superficial level of understanding these kinds of things. But when you get into the real world, where you're dealing with very complex problems, and you're dealing with very complex processes that are very sensitive, you have to make those kinds of distinctions and realize, okay, the limitations, especially when we get into radio frequency and very subtle, high voltage, high frequency, we can have very sensitive matters. And so when you're troubleshooting this negative energy in a typical circuit and you want to eliminate it, you have to be aware of those things, right? And so this is a meter that indicates generally what's going on, but you have to think about it that way. Don't assume that this is, like if you have this across the battery, that you're not in a separate loop. So, I mean, granted, it's going to give you a pretty accurate understanding of what's going on, but it's got its limitations. And you can see when you're doing very subtle things, what happens when you actually remove that very small shunt, if you will. You can see it makes a difference. And so putting a shunt amp meter, for example, in line with the charging battery is only telling you what's happening in the shunt. across the shunt. It's not telling you what's happening in the charging battery. And you can verify that by considering over time the rate of charge and the discharge rate of the battery over time, and see that it doesn't add up. So we don't ever use a shunt or leave a shunt amp meter in line with the output loop. We can do it often in line with the negative terminal on the input battery, but I tend to use the clamp amp meters because there's no real purpose for leaving a impedance in a line like that. And the problem is what we're doing with the circuit is allowing some charge to go back to the primary battery. And we'll talk about that in a minute when we talk about this added capacitor, which changes the whole dynamics of things later on here in this video. So let's see now. So we were talking about the MOSFET being changed. So I want a robust MOSFET that can handle high avalanche current, fast rate of change, and not blow out, and be high enough voltage. So what I've done is gone up to the MOSFET that I sell with the big motors, and I think with the bigger motors I'll probably end up going with a much higher, more costly MOSFET to do the same kind of upgrade. The faster the rate of change and the faster higher the voltage, the more the amperage that you need to cover that very fast high voltage spike. So the problem is most of the oscilloscopes that people use, like this one is my cheap one that can only show you so much. But if you have, ones that are in the gigahertz, which I have, then you can see, you have to have a probe that can be was rated for the gigahertz. Then you can see the spike goes way up there, and it's because these can't actually show how high it goes. So the question is, can the part handle that? Even though it's such a short on time, can it handle it, and will it blow it up? And ideally we want no dampening effect to have the maximum gain. We're just opening up a door with that spike, that leading spike, boom, that just all this energy flows in to all the impedances. And then you can see minor ripples in which those are minor events like that as well. So in order to do this in a way that is not too costly, we have to put some dampeners on that to some degree. So what I have is the limit here is 500 volts, and you'll see it will go over 650 volts. And so what we've done is, first of all, allowed for a higher spike across the MOSFET. So the drain and the source. So the drain and the source terminals of the MOSFET are going to get up easily to 650 volts. Now I have a capacitor across those terminals as 1,000 or 1,200, I think 1,000 or 1,200 volts, and it's right now is only 0.01 microfarad, and that helps to cut off that spike or dampen it across the MOSFET. And I don't have anything like this diagram across the output, and we'll talk about that I guess right now. The TVS diode rated at a high voltage will be, it's like a flyback phenomena here, where if you had disconnected the charging battery, this would activate. So that's something you can add on your own, and I will put parts on my website that you can order that separately. I'm not going to provide that because I don't want to have to try and explain that to everybody who buys a kit. They're on their own to do their own safety, like fuses, circuit breakers, and all that. I can't really provide that because if you run this at different voltage inputs, different power levels, you would have to have different parts for different fuses and so forth. So I may provide a circuit breaker in the future, but I haven't decided on one that can be used for 12 or 24 volts like we're running this motor. So we have a 500 volt MOSFET that has 100 amp capability plus avalanche current for short duration pulses. You have the data sheet will show you the difference between the pulsing you can do repetitively, the maximum, the safe operating area of the MOSFET, and then the one-time only pulse, which you'll find at startup to be probably, the biggest example of that. Because once it's all going, you don't have that initial startup. Anyway, so we have a 2500 watt power dissipation rating on this MOSFET. That doesn't mean that's all the energy that can flow through it. That means that's the energy that it can dissipate. Anyway, if you look at the data sheet, depending on the voltage and the amperage, it can get up into the 3000 watt range. But that's when we're turning on this, that's how much energy could potentially manifest, or we don't want to come close to that with this smaller motor. But I felt like I tried these other ones that could probably just sneak by, that were really good MOSFETs, but for the price, this one was a good one, and it's considerably low resistance, so that the internal resistance of the MOSFET is also going to be part of your loss. So if you have some of these really fast switching MOSFETs, like one my customer has very high resistance, and so there's going to be a lot of heat in that MOSFET, which is what you have to have a heat sink for. I'm trying to avoid all that. So this is kind of my best option that I've been using over the years, this bigger MOSFET for the bigger motors. So I'm going to include that with the kit from now on, even though I have hundreds of dollars of the older MOSFETs left in my inventory, and I would be tempted to wait until that was sold before I do this change, but I really wanted to make this available to people right away here, because I don't believe in, I'm not here for profit, I'm here to try and give the best solutions that I can under the circumstances. So in correspondence with that, we have the updated diode here, and it's a double diode, which I'm bringing together. So it's a 50 amp diode. So I think two 25s that are joined together. So it's a 50 amp 1200 volt diode. And I was spending a lot of time evaluating other diodes, and this one has worked out really well. And again, you have to deal with the same factors. So this is this D1 here. So this will be included with all the kits. And so that allows for practical results here for the cost. These are both pretty expensive, about $15 for the MOSFET and around $20 for the diode, which I get in bulk for cheaper, but it's still pretty expensive. And so I'll make those available on the website. And then we have, in addition, another kind of, it's not really a dampening process, but it does bring down the spike across the MOSFET a couple hundred volts down, is this same capacitor that we're using here, which is low ESR capacitor. We were running that at, that's 450 volts. And so that is across the, like I said, the coil input, the positive end of the coil, and the source terminal on the MOSFET. What this does, this allows, it's like a filter, it's just like you have on your circuits. Like here we have on the Arduino board several capacitors that are to keep the power more regulated, rather than powering it from you're powering from an external source down the line, and you want the power to be right there to be delivered. So what happens is there's a lot of back pulsing to the primary battery, like I said, and which then gets absorbed into this capacitor and made available. So you're not kind of fighting the current back and forth. You know, you're not having that lag time and all that. So that makes a noticeable difference, but it also was an indirect way of, or a direct way of, dampening the pulse across the MOSFET. And then that gets charged up and discharges into the circuit. So you get a better gain from doing that. So those are the updates here for the circuit, and you could expand upon that. So one way to expand upon this, if you want to go and push this harder, this whole system, then you have to up the capacitance directly across the MOSFET to protect this this MOSFET. Now it has its own internal diode which can handle, you know, the spike to some degree, but we'll see it'll be up to 650 volts, and it seems to be fine. So I'm going to leave it at that, but you could, if you're worried about that, you could change this little blue capacitor, say 0.1 microfarad instead of 0.01, like I have it. And then that would dampen that spike even more and get it down maybe to the 500 limit. Or you could use a TVS diode. Like I was saying in my last video, I had a TVS diode in series with that capacitor. So that's up to you if you want to do that. but this is the way I'll have it for now. Now I've made this double spaced, and it's sufficient to run this with a double spacer. So we'll try it both ways. Right now I've just made this with the double space, and so yeah, that's really what I was going to share on that end. You have to retard the timing, which means after top dead center, to get this started, and then you can turn up the power. So you turn down the power by, or the on time, by adjusting the potentiometer here. If you turn it all the way to the right, you're on full power, which I've limited because I want to make this for 12 and 24 volts. So I've limited, when we do the 24 volts, I want to limit that so that if you were to turn it too far, when I don't limit it, then what would happen is it would possibly blow everything out, because it would be overlapping the on time with the incoming magnet, so you're kind of fighting against itself. So as you go up in voltage, 12, 24 volts, 36, whatever, you're going to have to limit that on time more and more and move the Hall over somewhat more retarded, because the timing adjusts, and that relates to the RPM as well. So as the RPM gets higher, so if you don't have a load on the physical, if you're trying to do the negative energy charging, you're going to have a high RPM, you're going to have to adjust your Hall to where you want it, ideally. So I'm doing two purposes with this motor. That's why this video is going to cover that both. But if you're going to load this down, the RPM is going to be lower, therefore the Hall is going to be in a different position. And I was going to do the dual Hall. I do have that as an option. I don't sell it as an option, but I can do that. But right now I've added so many things to this, I don't want to create confusion. And it's just, I've decided against it. So I could probably talk to people individually about that if they want to add that. But I will put the terminal there so that if you want to add the second Hall for a startup Hall where you don't have to move the Hall around, then we can talk about it. So all you'd have to do is replace the blue board underneath there with the different code that would have the second Hall. Anyway, so now we're going to look at the SCR Pulsar. So now instead of the negative charging is, well, we talked about in the previous videos. I can't really go over the whole thing because I have the whole video on that. The negative charging allows you to have the best charging. It will be the best for the battery over the long haul. And this is something that some of us have done for years, where we charge the battery negatively, which is really what this motor is doing with this high spike right now. With the new MOSFET, I think really over the last year we've been doing negative charging, so that might, if people have not the greatest results, because they've been slowly changing their battery over to negative, and so it's not really possible with a negative battery to run the basic system like we have here, apart from this, to rotate the batteries around. So that's what I've been struggling with, because I've been trying to give people a positive charge over the years. That is what they're after, because that's more of what they can understand. But really, as we went to the higher gate driver or the higher speed switching, not switching, the higher turn on and off switching, we're really creating more of a negative charge in that. And we had a capacitor across the MOSFET in which kind of is part of the discharge to create a positive energy flow. But really, we were putting quite a bit of negative. So at the moment of a switch closure, even if you didn't have this loop, secondary loop, if you have a switch closure that is in series, like I said, if we had a dynamo, which would be, a 2-wire, with the return, and we had a switch that we turn on, and we did not have this, you would still have this negative energy in the system that goes before the current flow. So every time you throw a switch, there's always negative preceding the positive energy flow. And the negative is in all ways opposite to the positive. And this is an oversimplistic way of saying all these things, but that's all I can really share in this long video already. So you have everything opposite, as we talked about in the other video. So instead of the energy, like I said to somebody, the energy comes in like a vacuum cleaner to the negative impedance with negative. So it's coming in from the environment. And what's happening is you're kind of like creating an opportunity. You're creating a trigger. It's not that energy is flowing out of something and packets of energy are coming down the line and coming into this battery. It's the other way around. It's the energy is coming into it. That's the way you got to wrap your head around it. Otherwise, if you think in terms of current flow, like the positive energy, you're always going to underestimate it and misunderstand it. So now the current is passing down this line and it catches up, and in the presence of the current, there is no negative. They just mutually exclude each other, and the positive is dominant. It's not really dominant, it's just in the time, in relation to time. So the current is representing not only constant current we're talking about, but changing current. You have an impedance in the line in which has its own impedance, right? Its own opposition to current flow. And so initially it's very high and then it lessens. But during that whole time, where it's actually allowing any current flow, there is no negative energy. So this is why we do faster switching, to multiply the negative events and minimize the current flow, because we want this very fast changing field, or changing, switching. And that's where it's all at. Now, to run a motor, you have to have some current in order to make the coils operate the way you want. So that's what we're doing. Now, so we have negative energy flowing in the sense of coming in from the local environment to the impedances. You think about it in the way in terms of triggering. What happens in the battery is there's no losses in that process, whereas with positive energy flow, there's always losses. So when we do the cap pulsar, we also have the capacitor charges up itself with the negative converting to positive. The other side of the capacitor plate has the positive energy manifesting according to the theory, and then what we do is we discharge that into the battery through the SCR in the circuit just with the diode. Now if we want to get a higher voltage, usually that gives, if I have a higher capacity capacitor, we usually have about 1 volt across the battery. Here I think we're going to do about 4 volts. We'll look at that voltage across the SCR, and so the capacitor is pulsing 4 volts at 100 microfarads very rapidly into the battery. Now that is also creating a negative pulse preceding the current flow. So that is where the gain is going to be had in the fact, well, the fact is that the capacitor is going to charge up when it's not supposed to at all, according to like the amount that is charging up under the circumstances. If we were to believe Kirchhoff's law was universal, then we would really have nothing significant happening in this capacitor that we could ever use, but in fact we do. But if we look at the rate of charging and discharging this capacitor compared to the rate of charging this battery, that does not add up either. So there is still a negative event followed by the positive charging of the capacitor. Now, I used to do these big capacitors like I have here, and do it at a 1 volt difference across the battery, which is all right, but now I'm tending to rather do low microfarad for the health of the battery. You don't want to slam the battery with capacitance charging. That's what will kill the battery over time. So I prefer to use a gentler charging when we're doing positive. That's representing positive current. You don't want to hit, that's where the Tesla switch damaged the battery, especially when it went all the way from charge to discharge back and forth. So if you do it with low capacitance more rapidly, then you can get it right. So this works out fine, and it's a gentler charge, but it's still enough to give you the ability to rotate your batteries around. And so these batteries are kind of in a mixture. They've been somewhat negatively charged over the years with all the different things. So they're kind of in a state of, what do you want to do, Rick? Like, in other words, right now I'm going to go to positive charging them, and so they're going to respond slower because they have somewhat of a negative charge built up in them over time. So anyway, I have been charging them at times with the battery charger that does produce the positive current. You can see when I have a battery that's been negatively charged from, like I use these just for my videos in my conventions. So periodically I'll charge them up, and they'll charge to like about resting like 13.7 or 8 volts. But when I have negatively charged them, it will take a lot longer to charge them up because it's got to convert it back to positive. So some of you are rolling your eyes and you're laughing and you're whatever, thinking I'm a fool, don't know what I'm talking about, but I've been doing this for a long time, and I know by experience these different things that I'm talking about. I mean, I'm not expecting people to believe that. I'm just, for those who have been doing this, I know you'll appreciate, you know, like the comment that I read, they'll appreciate the details that I'm trying to share here. For those who are just wanting a 5-minute video, go elsewhere because it's not for you. This is about trying to share as much information as I can in a practical way. So the negative charging, again, the benefits are that there's no losses in it. The bigger the battery, the more charging manifests. It will happen too with the positive charging because there's still a negative element into the pulse that will benefit from a bigger battery, but not as much if I remove this. That'll have a greater possible output after the batteries have been charged over the same amount of time, the same running of the system. If you convert your batteries over to negative, they have most of the benefits are on that side. The only disadvantage is if you don't use the charge, it will discharge quite rapidly compared to a positively charged battery. So that's one of the issues that, as I talked about in the previous video, if you charge it with negative and turn the motor off, it will continue to charge for a set period of time. It can be as much as a day under certain circumstances, or it can be as long as only 15 minutes. And at that point where it stops charging, it will start to discharge. Not fast like, you know, that will be drained in minutes or hours or anything like that, but it will be noticeable compared to a positively charged battery. So it's more for people who are going to use it right away rather than charge up a battery and let it sit for days and weeks. So that's kind of the difference. We talked about anti-gravity, we talked about other benefits of the negative charge. The benefits of the positive is that you can store the charge longer, and then you can use it on the front end to drive the motor. Now, what I'm doing here with this capacitor across the input is kind of a step in the direction of creating the situation where a negatively charged battery could be used on the front end. So if you create a filter where the capacitance changes the energy, like I don't understand exactly what happens to a negatively charged battery, and I can't explain why that battery can't power the motor and create the charging in the other charging battery, why that doesn't work. I mean, why it's so different. That's something to read about from Tom Bearden or others talking about what's going on. But if you create the right type of circuit, you can convert it, which I'm not getting into. It's not my objective to get into that. That's kind of more proprietary information. But it's moving in that direction with this capacitor here. And I'll just leave it at that for now. I've demonstrated that a couple of times, well, at least one time in the public, where I was running multiple motors in series with each other. And there's a way to do that. So having said that, we can actually start looking at this running. So it should be all good to go here. So right now, there's nothing special about this. These are just wire connectors that I have here. Hopefully they don't touch each other. I'll be removing them to do the negative charging probably at some point, or at least with the other model, this one here. So we'll see that the amperage goes up a good deal at startup. And then it's not really important to show the loads at this point. I just wanted to go over kind of the upgrades. So right now I have this position. I have little dots where the magnets are on the rotor. And I have this position about a 1/2 inch after top dead center if I'm going to do the clockwise rotation here. And so we can look at the spike. I'm going to look at the spike because I can't see the amperage. Let's start up here. So it went up to a good 500 volts there. And now it's down. I'm not sure where you can see this. If this is in the way or not. So you can put a heatsink on this MOSFET if you're going to really push this hard, but I wanted to use the big MOSFET so that you didn't have to. And so when I was using some of these other MOSFETs over here, I found that I was really pushing them a little too hard at the startup there. So you can see that the charging is taking place here. 12:15 from 12.2. And if we look at, like I said, I don't have anything tricky here going on. This is just the way this is kind of sitting here. But if we go and look at the before and after, we're at 1 volt. Oops, I got this backwards. 1 volt across the SCR. 1.2 volts. But that can get up there because we're not really loading this down right now, so we have very little amperage. 1.9, I was getting it down to 0.2. So I have it where the Hall is set up where it can be in a reasonable position after startup. But we can see, so this is this leading spike right here on the off time. So we can see it's right. We've got 70, 80 volts only, so it's reasonably far down. And then as I change things, so I can I'm actually at full power here. Now I can change the position of the Hall and push more current. In the motor. or we can load it down with the generator. And I have a 100-watt LED. You notice it's speeding up because even though I'm at 0, it's still shorted. And I'm blinding myself here. So we have the bulb is pretty much at about the rating of the input. Now this one is double spaced, so this is more for a faster RPM. It's set up. We can take these off and show it running at the single space, but I wanted to show both of these. Well, this one I'm only going to show at the double space, and this one I'm going to show both. Because this one is normally at the single space, the single spacer instead of the double spacer. But this one's a lot harder to get started with the single space, and I just didn't want to push things too much. The customer could change that. So as I turn this up, the light gets kind of too bright for me to look at here. And of course, the same things. Why we still really haven't gone up too much more in amperage. But if we lower if I put more of a load on this, you can see the spike gets higher. I can't do it without burning my hand any further. But you can see the charging rate. Of course, the amperage changes. So we're at 3.5, 4 amps, 60 watts around. We have in the input battery, we have 12 volts right now on the input battery. So this is not exactly characteristic of where you're going to be starting off at 13 volts or whatever. But I wanted to show this more of a higher RPM. So if we were to short out the SCR, well, yeah, it wouldn't matter then, because we still have the capacitor there. Have to disconnect these. So let's do that. Let's stop this. Now, whether I was going to do the 24 volts first, but it spins really fast. If we run this at 24 volts with a double spacer, this is really, really fast. So for sake of time, I think I'm just going to go over to the negative charging. So we'll disconnect these wires here, if I can, with this tiny little screwdriver. Without shorting my terminals, which I tend to do. without damaging my SCR, because I don't really have it on any kind of thing that protects it from bending its legs. Oh, I've made this so tight I can't even do it with a screwdriver. If I had... Oh, there's my other screwdriver. Definitely want to do it. My funny German phrase that I made up. Guten tight. I wanted to make it really good and tight, which is not a German word, but I make it sound like a German word. Guten tight. Oh, see, I did this yesterday. I wanted to put the black wire into the positive. It even happens to me all the time. So what we want to do here is just do the negative and look at all things equal. All right. So now we have the battery. For some reason, okay. I should put a wire on there to. So it's come back down 1212, but it has charged somewhat in that short period of time. It would still continue to come down, but let's see if this is still at 0. See, it's goes out a little bit. So now we're going to. We have this shorted, so there's no load to start it, and it should start up just the same as it did last time. You can hear a little tick, and let's look at, now there's a much higher spike, because the capacitor is not there in the line. And we have a regular spike that is higher than the other one was. So let's turn this, whoops. Let's turn this on. So you can see the voltage is climbing a lot faster with the negative charging because the spike is higher. So the voltmeter is not really measuring the exact battery voltage, it's measuring the spike and the voltage and trying to sort out the difference. So in other words, there's a lot more happening across the battery. It's very similar to what it was without the capacitor because there's a small capacitor. So let's turn this on again, and we'll see that. And it's loaded down, and all those things are the same. So, not my objective to prolong all this. So let's try now. I wanted to just show the capacitor on the first setup rather than when I go to 24 volts and all that. So right now, what we're going to do is set up for 24 volts here. And we'll move everything around. All right, so we got to reposition these batteries here in a way that I can do at 24 volts. So I had them like this. I had this one like this. And then this one comes around here. That way all goes together. So you want to double and triple check your work as a mechanic. You had to triple check your work, especially when you're doing an oil change. Did you forget to put the oil filter on or the drain plug back in? Did you put the gasket in the drain plug? It happens. If you're using the Bishop's oil, though, you don't have to worry about that. It won't damage the vehicle. Anyway, let's move this stuff out of the way here. (24, 23), that should come down a little bit. And then let's connect this in. And this is what you want to really use rather than clips. I think I might not include clips anymore because I'll probably include them, but I want to draw attention to not using clips. All right, so we're going to move this back out of the way. So what I'm going to do is start off by turning this down. We don't want too much power at startup. All right, so everything's good. 24 volts in, 24 volts out. I'm going to put this at the 100 amp setting. And hopefully we're all good to go. So in this case, probably have to bring this down to 100 volts to see a rather large spike on there. So this probably won't start up until I turn it up high enough, but we'll see. Yeah, so we need to turn up the power a little bit more. Probably advance the timing more too. I'm just going to look at this while we're doing this. So it's kind of a play on where you position the Hall and how much you turn the pot up. So we have 200 volts right now, and only 1.3 amps. So we can turn this on and run our load. And then we could crank this up. So I'm at full now. Again, we're never going to push that much amperage with the double spacer. So if I could push this up so that we're pretty much at, so now I could push more current as I move the Hall over. You have to be careful with that. You don't want to move it over too quickly and go too far. But see, now we've gotten into such a high RPM that it's literally lost its gravity in a sense. It's created its own, it's like a gyroscope. You can feel, it's a really weird feeling here, but it can literally vibrate itself off. So this is really, really fast. This is it's set for 2 microsecond intervals, and it's really at about 1 microsecond between each pulse. Anyway, you get the idea. So we can load this down a little bit. I can't do it very long, it's going to burn my hands. But so we're only at 1.6 amps here. Now again, if we were able to load it down, I could load it down with a different load on here, but that's not my objective in this video. Anyway, that's very fast. So that's that motor with the double spacing. So what I'm going to do is stop the video right now and make this a single space. All right, we're back here, and I just had to verify that it was going to work. So what we've done then is reduce the spacer to 1 spacer, and I think what happened was I started, when I'm using the most powerful magnets right now, and before I wasn't, for good reason. So this is a lot more torquey than it normally has been, because the set of magnets that I got were N52s, and I think there may be even higher than that, if there is such a thing, for the neo magnets. Anyway, it kind of threw me for a loop, because I wasn't able to run this very easily, and I was experiencing some problem that was kind of a mystery to me, and I didn't know what it was. But I think it was the magnets being too strong. But anyway, let's start this up, and we'll just see it run again like it's supposed to. Oops. So we can see that the spike was pretty high up there, 300 volts or so. And again, I wanted to set this up so you could do 12 and 24 volts. So the 12 volt is what people will normally be working with, and I've limited the code so that you can only turn it so far before it starts, so it doesn't ever overlap when you put the Hall in this position. So we can turn this up now that I've started it. You can see the amperage wasn't very high at startup. See, I just get to the point where it's at its limit. So even, this is kind of scary too, very fast. Good charging rate. Now we can turn this on and load it down. And it's kind of screaming at us. So we can load this down a lot more. If I put more capacitance across this, it might change it. So that's all. I could play with that for a while and do all that, but or we could run the bigger light. So we have another, we got the 400 watt light here. So that wants to be run at certain RPM and all that. So anyway, we're still only at 3 amps. If I push this, so if I adjust this and the load, of course my charging rate goes up and all that. But anyway, I didn't really want to deal with the loading right now. Essentially, I just wanted to show the, I wanted to show the way the system is right now. So what I'll do is bring the camera over now in order to do that, because before I get into this one, I might as well show what it looks like here. So I'm going to have to take my microphone off here so I can actually walk around with the camera, but I'll leave the microphone there so you can hear me. Alright, I always cover the lens. I don't want to do the shaky camera syndrome. Alright, you still need to speak into the microphone, so I will hold the microphone here, and I can see that I'm still... so what we have is, again, the green capacitor there is across, well, get the schematic here. So you can see that capacitor right there is connecting right here. The positive and the negative is this wire going, which is parallel or connected to the same wire here underneath the board, which is connected to the source terminal right here of the MOSFET. And so you can see here the little blue capacitor here, and like I said, you want to upgrade that. If you're getting too much spike across the MOSFET, that has to be increased. So down the road we'll, you know, get it all detailed out as to which for what you're doing. We'll do subsequent videos. So anyway, here's the big MOSFET, 500 volt, 100 amp, 1200 or 2500 watt MOSFET. This is the 50 watt, 1200 volt Schottky. Very good, very, very good diode. So these are not getting hot at all. Not hot, but I mean they get a little bit warm, but not much because we're not really pushing them too hard. And oh yeah, the position of the Hall, you can see I did move it a little bit here and there, but that's the position. I mean, I don't put dots on these, but I wanted you to see that. So again, this is rotation, and it's very tight. It's very hard to turn this, but once it's spinning, once it's moving, it kind of glides. It's really a little bit tighter than I want it to be, the way we've usually had it, but that's because the magnets are so strong. So for that, we should probably put a little bit bigger spacer in there. Anyway, that's for now. We can maybe hook up this bigger motor next, and that will be right after. All right, so now we have the double stacked with the double spacing here. It's kind of hard to run this with a single spacer. You can take them out, but you'd have to move all the layers around. So let's get it started. So I have it really far turned down and really far advanced with this double stack. It's a bit of an animal to get going. So here we have 2 amps. Now what we're going to do is speed it up. So it's a bit of an animal to get started. So we have 140 volt, 150 volt spike. This is just at 12 volts now. Now if we want to, we have to advance it now. So this one's probably going to need more of the double Hall. So anyway, you can see it's charging the battery, of course, and it's got an output. So that one is a good bit advanced. Again, about 1/2 inch, and I had to start it really low. So it's always best to start it low and see what it does, and then work your way up, get familiar with it. So I don't know if I'll have time here to do the 24 volts or not. Here, we'll see what I can do here. Kind of running out of time. Long videos. So if we hook this up, (24 volts). It's a lot easier to start this because I'm making the code for 12 and 24 volts. It's a bit of an issue to balance both of them. All right, so that was at a very low setting. All right, so let's start that up, hook it all up. All right, so we're about 1/2 inch after top dead center, and we're pretty low on the potentiometer. So we got 3 amps here. Now we can crank it up. This is where we need the high voltage parts. As you can see on the scope, it's already at, you know, at startup it was higher. I didn't look, but it's quite a bit higher. And let's make sure my microphone is on. Good. All right, so now we can see we're only at 2 amps. Again, we're not loading it down very much. So now we can crank it up and adjust the Hall, so forth. So we're nice, good voltage there, good charging. And we got 3 amps, 24 volts. You can look at the voltage. Oh wait. .16 volts between the 2 batteries, or between the front batteries. And 25 volts pretty much on the charging battery. So we got some really good beneficial charging. And again, we can add the positive charging with this SCR circuit there. So again, I can continue to crank this up and rotate the Hall and so forth. But what I want to do is turn it back down so that people can start it up. So it's all ready to go to start it up. So there it is. It's all ready to go. So I think that covers everything here that I can think of. And this one's a little bit harder, the double stack, to deal with. And what we'll be doing with, there's only a few of these that are going to get these strong magnets. It's more problematic to deal with, but it's more powerful potential. It's just the fields can tend to overlap each other more when you have more powerful magnets. So most of the orders get the weaker magnets because they are very strong already. So anyway, that's all I wanted to share now. So thanks for watching.